reactions and some practice examples, and that's what I'll be covering on Monday. So if you want to have that handy, it might be helpful for you. And then whatever time we have remaining on Monday after we finish up organometallics, we will get into amino acids and proteins. Okay. Does anybody have questions on the schedule or anything like that before we get started? Okay, then why don't we go ahead and jump into carbohydrates. All right, so the carbohydrates are going to be the first of the molecules of biochemistry that we're going to get into. This area, this part of the course with the focusing on biochemistry is we're just going to kind of scratch the surface of it because in reality, most of you, if not all of you, are going to go on at some point in your future and take an actual biochemistry class. So we are just going to do a little bit of an introduction into the molecules of biochemistry and look at it from a slightly different perspective than what you're going to get when you take a real biochemistry course. And that is, we are going to look at it, not surprisingly, from the organic chemistry perspective. Meaning that all of these molecules that you're going to encounter and study extensively in biochemistry are nothing more than organic molecules. And if you can kind of view them in that perspective, it's going to allow you a great deal of predictive power. Because in the end, they're just molecules with functional groups that you already know. You've studied aldehydes and ketones extensively. You've studied amines quite a bit. You've studied carboxylic acids quite a bit. So all of these functional groups you already know, and you know how they react. Now, granted, the molecules are going to get bigger and more complicated and uglier, but they're still just organic molecules with functional groups you know. So if you can kind of view them in that way, it will allow you a lot greater ability to kind of understand them and, more importantly, predict how they're going to react. Okay, so that's what we're going to do. We're going to focus on these few of these biological molecules and look at them from an organic chemistry perspective. Okay, so the first ones that we're going to look at, and by the way, the other thing that we're going to do is we're going to focus on these kind of the small version at first, and then build up to the polymeric version. Most of these molecules of biology are actually biopolymers. If you think about polysaccharides, proteins, new strands of nucleic acid, DNA and RNA, all of these are polymers of a specific monomer unit, be that nucleotides and nucleic acid, amino acids and proteins, or monosaccharides and polysaccharides. So the way we're going to go through this is we're going to focus on the monomer unit first, kind of get an understanding of that, and then we're going to build them up into the big biological polymers that most of these exist in nature. All right, so let's start with the carbohydrates. Okay, so we're going to start with the carbohydrates. When we talk about carbohydrates, this is what makes up a good chunk of most people's diets, and this is the stuff that is so good to eat. Basically all the sugars, right? So any kind of sweet things that you like, you can thank carbohydrates for. This also includes all of the starchy foods, like breads and pastas and rice and starchy vegetables like potatoes. So all of this is carbohydrate. You can always tell a carbohydrate, by the way, because they have a very common ending. Okay, the suffix of virtually all carbohydrates ends in OSE, right? So if you think about the sugars that you're familiar with, you probably are familiar with glucose, blood sugar, fructose, fruit sugar, sucrose, table sugar. And you notice a trend. All of them end in OSE. So anytime you see any name that ends with OSE, you can bet that you're dealing with a sugar, all right? And by the way, I'm going to use those terms interchangeably, carbohydrate and sugar. I'll kind of use them equally, interchange them. They're referring to the same thing, okay? When we talk about a carbohydrate from a chemical perspective, really these are nothing more than polyhydroxylated aldehydes and ketones. All right, so that's all a carbohydrate is from a chemical perspective. When we start talking about them, we can really classify these carbohydrates on the basis of how many monomer units are present. So as I said, we're going to focus initially on the monomer unit, namely the monosaccharide. All right. But in nature, it's much more common to find them in polymers. So if you have two of them together, you could call it a disaccharide. Three of them, a trisaccharide. A few of them, like say under 10, you could call that an oligosaccharide. And if you have a big polymer of them, say hundreds or thousands linked together, we call that a polysaccharide. So we can kind of classify these on the basis of how many individual monomer units are put together, right? The other way we can classify these, we can classify the monosaccharide unit. And the way this is commonly done is either on the basis of functional group or on the basis of carbon number in the monosaccharide unit. So for instance, if you're dealing with an aldehyde sugar, we can call that an aldose. If you're dealing with a ketone sugar, we call that a ketose. And then if you want to classify by carbon number, if there are 3 carbons in the chain, we call that a triose, 4, a tetrose, 5, a pentose, etc. Right? Now the thing I want to call your attention to is this one, because this is where people get it mixed up. You'll note that when we're classifying according to carbon number, we're using strictly Greek prefixes, not IUPAC. If you have a 4-carbon monosaccharide unit, we do not call it butose, right? Strictly by the Greek prefixes. Okay? So, if we're looking at the 2 monosaccharides below, this guy here, we can see that it is an aldehyde. So this would be considered an aldose sugar. If you count your carbons, 1, 2, 3, 4, 5, 6, that's 6 carbon chains, we could call it a hexose. Oftentimes what you'll see is you'll actually combine those. So to give more information, you can combine the functional group and carbon number classification and just call it an aldose hexose sugar. Okay? What about the next one? Is this an aldose or a ketose?
Ketose.
Yeah, it's a ketose because the carbonyl is in the middle of the chain. And how would you classify it according to carbon number? Yep, there's 4, so it'd be a tetrose. So we could combine that and call it a ketotetrose sugar. Now, by the way, are these monosaccharides chiral? Do they possess chiral centers?
Your green star.
Yeah, it looks, yeah, I forgot to erase my green star. It kind of gives it away, right?
Yeah.
But, so yeah, that's a chiral center. You look at, this is glucose, by the way. You look at glucose, and it's got 1, 2, 3, it's got 4 chiral centers. So these are, the vast majority anyway, of monosaccharides are going to be chiral molecules. And as a result, let's start with a very simple one. This is glyceraldehyde. You'll note that it has a single chiral center at the C2. And so if you put glyceraldehyde next to its mirror image, what you'll notice is that they are non-superimposable. So this would be one enantiomer of glyceraldehyde, and this would be another enantiomer of glyceraldehyde. They are not the same, they are non-superimposable mirror images. Okay? Now, you can, like any molecule, you can represent these chiral species with wedges and dashes, as shown in the slide, but it becomes quite tedious to do that when you start getting into 3, 4, and more chiral centers. So what we most commonly see with these monosaccharides is instead of representing them as wedges and dashes, we're going to represent them as Fisher projections. So if you recall, a Fisher projection is going to represent a chiral carbon as a cross. So we have one chiral center in glyceraldehyde, so I'm writing one cross. Remember, you want the carbon backbone on the vertical. And you want the highest oxidized carbon to be on top, or as close to the top as it can be. So that's why I've drawn the Fisher projection in this way. You'll note you have the one chiral carbon, so I have one cross. I have the highest oxidized carbon at the top, and the carbon backbone is on the vertical axis, not horizontal. Okay, those are kind of the customary rules of Fisher projections. Now, when we talk about the sugars, we classify them on the basis of their stereochemistry. So you'll notice that this version of glyceraldehyde has the chiral hydroxyl to the right. When you have a situation like that, I'm going to refer to that from here on as a D sugar. That's why I have this capital D in front. If, on the other hand, that chiral hydroxyl is to the left, as in the mirror image, I'm going to refer to that from here on as an L sugar, which is why this has a capital L out in front. Okay? For whatever reason, back in evolutionary history, nature chose one of these to deal in. The vast majority of monosaccharides in nature are D. There are a few exceptions, 3, of naturally occurring sugars that are actually L, but the vast majority of monosaccharides in nature are D sugars. Okay. And so let me, just to give you some examples, I have the common mono, no, oh, sorry. I did forget to tell you one thing. When we're talking about capital D, capital L, a lot of times people get this a little bit mixed up, because you already learned about D and L last semester, right? You learned about, in the context of optical rotation, the way that these chiral molecules interact with plane polarized light. That was little d, little l, right? Dextrorotatory, levorotatory. It turns out this D and L has absolutely nothing to do with little d, little l. Okay, this capital D, capital L that we use in the context of monosaccharides is a stereochemical thing, having nothing to do with optical rotation. So you can have a D sugar that rotates like levorotatory. Okay, they have nothing to do with one another. All right. Any questions on that? Okay, so on the next slide, I have a bunch of examples of the D sugars. You obviously don't need to learn these for this class. You'll get that fun when you take biochemistry. But I did want to show it to you because whenever we were talking about the DNL sugars a minute ago, I said that the chiral hydroxyl was pointing to the right for a D sugar. Well, what if you have more than one chiral hydroxyl, as you do in all of these, and all of these, and these, and these? The one you're focusing on to determine DNL is the chiral hydroxyl farthest from the carbonyl. And so when you look at these, there's the chiral hydroxyl farthest from the carbonyl. There it is, there it is, there it is, there it is, there. You'll note all of those are pointing to the right, which is why they are D sugars. Okay? You can look at the same slide, looking at these guys in enantiomers. There's all the L sugars. And again, find the chiral hydroxyl farthest from the carbonyl on each of these. And they are all going left, which makes those L sugars.
And the reason why the bottom one isn't looked at is because the bottom C isn't chiral.
Correct. Yeah, exactly. So this CH2OH is not a chiral center. Okay, so far we've been looking at these monosaccharides in their linear or open chain. Actually, before I do that, I want to give you a quick example. So let's look at the most common monosaccharide. This is glucose. By the way, when I draw these, I will oftentimes omit my hydrogens, like I did here. They are obviously there. They didn't just walk off a molecule. But oftentimes, kind of like when you're drawing skeletal structures in normal organic molecules, we don't oftentimes draw in the hydrogens. Same thing here. They're still present. All of these guys have H's attached, but a lot of times I'll just omit them. Okay. So this guy here is glucose. If you look at the chiral hydroxyl farthest from the carbonyl, it's going to the right. So more specifically, this is D-glucose. Now, if I were to draw did I just draw L-glucose?
It's not the mirror image.
Yeah, exactly. Remember, D-glucose and L-glucose are enantiomers. They are mirror images of one another, meaning that all of the chiral centers must be switched in order to be an enantiomer. If you compare the two that I've just drawn here, I've only inverted one of the stereocenters. So they're not identical to each other. These two are not the same, but they're not mirror images either. So what is the stereochemical relationship between these two? If you're dealing with a stereoisomer that's not identical and it's not an enantiomer, what do we call it? It's a yeah, exactly. These are diastereomers of each other. All right. So yes, it is an L sugar because the chiral hydroxyl farthest from the carbonyl is facing left, but it is not L-glucose. Does that make sense? Does anybody have questions about that? Okay, then let's go on to the next topic. This gets back to something that I was talking about in the introduction. These compounds are aldehydes and ketones. So they're going to behave, even though they're a lot more complicated than the ones we've looked at in the past, they're going to behave chemically just like aldehydes and ketones. So in the same way, if you recall, if you take an aldehyde or a ketone and you added one alcohol to it, what did you get? What was the functional group that resulted?
Ester? No. Yeah, it's an ester.
Hmm?
Ester?
No. Ester is carboxylic acid plus alcohol.
Oh, okay.
Looks like that. Yes, it's a hemiacetal.
Okay.
And if you added a second, you got the acetal. Well, again, these molecules are nothing more than aldehydes and ketones, so they are going to behave just like that. Meaning, if you have any alcohols around the aldehyde, they can react to give you a hemiacetal. Well, look at that. You have the aldehyde, and you have a whole bunch of alcohols around. And so while so far we've only been looking at these in their linear or open chain form, if you put these in solution, the vast majority of the molecules are not going to exist in this open chain form. They instead are going to have one of the hydroxyls wrap around and attack the aldehyde or ketone. And it's going to result in a cyclic compound, specifically a cyclic hemiacetal. Now, in theory, any of these OH groups on the molecule can wrap around and attack. What's going to be the difference? What's going to be the difference, say, if the C2 hydroxyl attacked versus the C5 hydroxyl? Yeah, it's going to give you a different ring size, right? So if for instance, the C2 hydroxyl attacked, you would end up with a 3-membered ring. So how likely do you think that is? Probably not very likely. We don't see 3-membered rings very much because they're highly strained. So when this process occurs, what ends up happening is because of ring strain, we're only ever going to see 5- and 6-membered rings. Okay. So you can see in the structure to the right, you can see that the C5 hydroxyl here is kind of wrapping around and attacking the C1, and now the C1 is a hemiacetal. Now, we obviously are not going to represent cyclic structures this way because it's kind of ridiculous, but the way we're going to start representing them is like so. This is what is referred to as a Hayworth projection. And the Hayworth projection, what it does is it takes the ring oxygen and it puts it in the back. And then you number around the carbon chain in a clockwise manner. Okay, so you can see, let's compare the linear to the cyclic form. The C1 was the aldehyde. It got attacked by the C5. So the C5, you can see it in red, the C5 hydroxyl becomes the ring oxygen. The C1, remember, it was the carbonyl. But upon attack, this guy is now hemiacetal carbon. By the way, as we go through this, we're going to see a bunch of kind of new terminology. Carbohydrate chemists have their own kind of lexicon. This hemiacetal carbon is given a special name. We call it the anomeric carbon. Or the anomeric center. So, how many chiral carbons did you have in the open chain form? Mm-hmm. 4. C2, 3, 4, 5. Those are your chiral carbons. 4 chiral carbons. How many chiral carbons do you have in the cyclic form? Yeah, 5. Because the C1 is now a chiral carbon. Right? Before, C1 was not chiral because it was sp2 hybridized. But upon cyclization, that becomes an sp3 carbon with 4 different groups on it. And so it is now a chiral position. So, what you see here is you kind of have in the middle the open chain forms of glucose, and it's just kind of represented a little bit differently. That we're kind of bending it around so that the C5 hydroxyl that's going to become the ring oxygen, the one that's doing the attack on the carbonyl, is kind of close to the carbonyl that it's about to attack. Okay? And because you have freedom of rotation about the C1-C2 bond, you can get the hydroxyl either going in a downward position, or you can get the hydroxyl going in the upward position upon cyclization. Now those two forms, with the anomeric hydroxyl going down or the anomeric hydroxyl going up, are they the same? Are they identical to each other? No, because one chiral hydroxyl is going down and the other's going up. So they're not the same. Are they enantiomers? Hmm? No, they're not, because we didn't do anything to the rest of the chiral carbons. The C2 chiral hydroxyl is down here, it's down there. The C3 chiral hydroxyl is up here, it's up there. The C4 chiral hydroxyl down there, down there. None of the other chiral positions have changed. They're all the same. The only one that's different is the anomeric. So what is the stereochemical relationship between these? They're diastereomers. They have one, but not all, chiral carbons inverted. These are given also kind of a special name. I'm not going to refer to these two diastereomers as anomeric up and anomeric down. Instead, what I'm going to call these, I'm going to refer to the one where the anomeric hydroxyl is up. I'm going to call that the beta anomer. And I'm going to refer to the other one as the alpha anomer. And I'll give you a really stupid mnemonic device that will hopefully help you never to forget this for the rest of your life.
Does anomer mean the whole molecule or just that carbon?
It's just referring to the C1.
Okay, so specifically that
Mhm.
carbon.
So the stupid little mnemonic device is that ants are on the ground and butterflies are in the sky. So A, alpha, ants, hydroxyl is facing down. B, beta, butterflies, the hydroxyl is pointing up. So, anyway, that's a way you can hopefully never forget it for the rest of your life. Let's go ahead and look at how to name these. So when it comes to naming cyclic monosaccharides, there are 4 variables here. And we've got to include all of them in the name, otherwise we have not unambiguously identified the cyclic monosaccharide. Number 1, we have to include the anomer. Is it alpha or is it beta? Second thing, you have to include the stereochemistry. Meaning, is it D or is it L? Now, I'll tell you, for this class, I'm only going to ever give you D sugars. There are very, very few naturally occurring L sugars, and so for this class, you can pretty much just assume if you're asked on an exam to name a cyclic monosaccharide, it's always going to be D in this class. Okay. The third thing we need is the identity. Is it glucose? Is it mannose? Is it fructose? Is it galactose? What sugar are you actually dealing with? And then finally, ring size. I mentioned a minute ago that when these cyclides, they're only ever going to give you 5 or 6 membered rings. So you have to specify, are you dealing with the 5 or the 6 membered ring? The way we do that is if it's 5, we call that a furanose. Whereas if it's 6, we call that a pyranose. So let me give you an example here. All right, so this is a form of glucose. And by the way, I'll also draw it in the linear form just so you can reference it. Okay, so I've drawn this glucose in both linear and cyclic form. Now we said, if we want to unambiguously name the cyclic monosaccharide, the first thing we've got to do is give the anomer type. So in the cyclic form, am I dealing with the beta or alpha anomer? Yeah, beta, because the anomeric hydroxyl is going up. Butterflies are in the sky. What is the stereochemistry here? Yeah, it's going to be D because, well, number 1, I told you that's all I was going to give you. But number 2, look at the chiral hydroxyl farthest from the carbonyl. It's to the right, meaning it's a D sugar. The identity here, we're dealing with glucose. and it's a 6-membered ring. So I'm just going to tack on pyranose at the end. So we call it beta-D glucopyranose.
Just a quick question.
Mhm.
If you're looking at the ring version,
Mhm.
and you're looking at like a hydroxyl group, if it's down, is it always going to be D as well? Or can you use that?
No.
No.
Mm-mm.
Okay.
Not really. The better way of identifying it is on well, it kind of depends. One of the more common ways of identifying D from L in cyclic form is where the CH2OH group. If the CH2OH group is up, it's usually going to be a D. If it's down, it's going to be an L. So that's one way of representing them. There's another, but like I said, I'm only going to give you the D monosaccharides for this class.
So can this molecule also make a 5-member ring?
It can.
And will it?
Mm-hmm.
Like all, like in the soup of
Mhm.
the glucose, you're gonna have both things
Mhm.
happening?
Yep.
Okay.
Okay, so let me give you one more, and then we'll move on from this. Let's see. Let me give you this one. I guess I don't need to give it to you in open chain form. Let's just do this. All right, so this is D-ribose. So let's see if we can come up with the unambiguous name. So, start with anomer. Is it alpha or beta? It's alpha because the anomeric hydroxyl is facing down. Stereochemistry for this class is going to be easy because it's always D. The identity of the sugar is ribose, so I'll call it ribo, and then it's a 5-membered ring. That makes it a furanose. All right. Any questions there? Okay. The other thing we need to be able to do, in addition to name these, is convert these. Meaning, if I give you an open chain form, you need to be able to draw the proper cyclic form. So it turns out that that's pretty easy to do if you follow 2 rules. All right, so let's go back to glucose for a minute. Well, let's switch it up. Let's deal with mannose.
How are we gonna know what kind of sugar it is? Are you always gonna tell us what it is?
Yeah, I'll tell
Okay.
you what it is. Okay, so with mannose, we're going to convert this into its cyclic form. Now, the way we do that is a 2-step process. The first thing I'm going to do is I'm going to find the chiral hydroxyl farthest from the carbonyl, and I'm going to rotate its substituents. Remember, there was a rule back when you were learning the manipulating Fisher projections. One of the allowable motions was you can hold one of the substituents constant and spin the other 3. And that's what I'm going to do here. So I'm gonna hold the top of the chain constant, meaning all of this top stuff is the same. So left, left, right. And then that bottom chiral carbon, I'm spinning the substituents. So now the goal of this is to have the OH on bottom. If I spin that, then that means H is over here to the right and CH2OH is to the left. Now what I'm going to do
I have a
is
quick
I'm going
reminder,
to,
or a question. We can spin it either direction, right?
you can,
Okay, just
Um,
wondering.
yeah, you can, I mean, but in order to get the OH group at the bottom, if you were gonna rotate the other direction, you'd have to go 2 times.
Right, but if we had an L sugar, we would want to rotate it the other way.
Yeah, yeah.
Okay.
Okay, in the next step, what I'm gonna do is I'm just gonna push it over, rotate it 90 degrees clockwise. So what that's gonna do is it's gonna convert my vertical Fisher projection to a horizontal Fisher projection. So if you number these carbons, you can see how this is going to work out. So the C6 is up there. So whatever was to the right in my Fisher projection is going to end up being on bottom in the horizontal. Whatever was on the left over here is going to end up on top. So C2 is up, C3 is up, C4 is down, and then C5, well, that's just the last one that has its OH group on the end. Then when I go to draw my Hayworth projection, I'm just going to draw kind of the skeleton of the Hayworth. This gives you the orientation of your hydroxyl groups. So C1, you can draw any way you want, unless you're told specifically otherwise. All right, because remember, when you have the ring closing, you're going to get both alpha and beta anomers. So unless you're specifically told what anomer to draw, you can draw this any way you want at the anomeric position. The other positions, however, are fixed. So C2 is going up, C3 is going up, C4 is going down, and there you have it. Any questions on this? All right, let's do one more. So this is galactose. So remember, the first thing that we're gonna do to convert that into a cyclic form is I'm gonna rotate the groups on the C farthest, on the chiral hydroxyl farthest from carbonyl.
If we're just looking at that first one, there would really be nothing to indicate whether or not we should draw it 5 or 6 membered, right?
Yeah, you would have to be told.
Okay.
All right, so I spun the substituents on the last chiral carbon. Next, rotate 90 degrees clockwise. All right, so my C2 should be down. C3 and 4 should be up. I'm going to draw the skeleton of the Hayworth. C1, the anomeric position, can be any way you want, unless you're specifically told. C2 is down. C3 is up. C4 is up. Questions here? If we wanted to name this, can we start with those 4 things, the 4 descriptors? In terms of the anomeric form, it's alpha. It's a D sugar. The identity is galactose. And it's a 6-membered ring. Questions there? Okay, so it turns out that there's a rather interesting phenomenon that occurs when you put these, you take, say, beta D glucose. If you were to buy a bottle of beta D glucose and you put it in water, an interesting phenomenon happens. Just kind of for the record, it turns out pure alpha D glucose has a specific rotation of plus 112. Pure beta, so the anomeric form, the anomer, has an alpha rotation of about 18.7. Is that surprising to you? If alpha glucose is 112, shouldn't beta be minus 112? Should it not be equal but opposite in magnitude? because enantiomers rotate plane polarized light equal but opposite, right?
But they're not enantiomers, are they?
Yeah, that's exactly the point. Just because we're dealing with two different, you have to remember, we're dealing with two different forms of glucose, but alpha and beta are not enantiomers. They are specifically diastereomers at one chiral position. Okay, so no, it's not unusual that they don't have equal and opposite optical rotation. So if you were to take one of these, let's say take the alpha anomer, put it in water, and you measure the optical rotation, you would get plus 112. If you came back an hour later, you would notice it's no longer 112. It will decrease. You come back an hour after that, it will have decreased even further. It will eventually reach an equilibrium value of about 53. So what that's telling us is something is happening to the chirality of this molecule. It is not static. What happens with these monosaccharides is a phenomenon known as mutarotation. Mutarotation is, what it's saying is that if you start with pure alpha anomer, like this, and you put it in solution, this hemiacetal bond is not stable. It continually opens and closes and opens and closes. Now, at any given moment, the vast majority of the molecules in solution, greater than 99%, are going to be in cyclic form. But they are continually opening and closing and opening and closing. And they are in equilibrium with the open chain or aldehyde form. And it's going to ultimately reach some equilibrium value. It's different for every monosaccharide. For glucose, it's about 2/3 beta, 1/3 alpha. But what this is saying is that in solution, at any given moment, you have aldehyde form. Why do you care, you ask? Well, because if you do something chemically to these cyclic monosaccharides that would affect an aldehyde, you're going to affect these cyclic monosaccharides. So for instance, if I were to take and, treat this, say I gave you a reaction and asked you to predict the product, and I said, take this, treat it with sodium borohydride. Well, you might be tempted to say no reaction. Because remember, sodium borohydride, what does it do? It reduces aldehydes and ketones. So you might say, you might look at this and say, well, there's no aldehyde or ketone there. This isn't going to react. But this, what you have to know, squirrel back in the recesses of your brain, is that anytime you have a cyclic hemiacetal, it is always in equilibrium with this. So if you treat this with sodium borohydride, even though it looks like there's no aldehyde, because there's not, the aldehyde is still present. So sodium borohydride will actually reduce this, which is going to pull equilibrium to make more of that. And more of it gets reduced, and then more of it gets made, and more of it gets reduced, and finally you end up with nothing but CH2OH over here. So you have to keep in mind that because of this mutarotation, the aldehyde is always present when you have cyclic hemiacetals, because that's going to dramatically affect the way these react. All right? So let's see what we can do with these. One of the things you know about aldehydes is that you can oxidize them. I've known this for a very long time. You can take a aldehyde, you treat it with an oxidizing agent, you get a carboxylic acid. Same exact thing here. If you have the aldose sugar, you have the aldehyde here. If I treat it with an oxidizing agent, I'm going to get a carboxylic acid. By the way, we call these an aldonic acid. Now you do have to be a little bit selective with your oxidizing agent. What would be the problem if I took this monosaccharide and I used something like permanganate? Would I get this aldonic acid? Yeah, exactly. You have a whole bunch of alcohols here, and as you know, permanganate oxidizes alcohols. So this would give you a holy mess. It would not be selective at all. You would, in fact, I don't know, you may have seen, it's kind of a popular demonstration they do in Gen Chem a lot. I think they call it like the screaming gummy bear. But if you take gummy bears, or, I mean, really any candy, because it's just the sugar that you need. I think they just use gummy bears for dramatic effect. But anyway, if you take something that has a bunch of sugar in it, and you put permanganate on it, it reacts pretty violently. It starts smoking, and it's exothermic, and it starts turning things black and tarry. It just makes a mess because the permanganate just unselectively just oxidizes the crap out of that. It's nothing useful. I mean, it results in nothing useful other than kind of something kind of fun to watch. But yeah, it's a very non-selective oxidizing agent. You have a lot of potential oxidizing sites. So if you want to do this conversion cleanly, you have to use a much milder oxidizing agent, and these are some of the more common ones that have been developed for monosaccharide chemistry. You'll note most of them are metal reagents, either copper-based or silver-based. Now, these sugars that can oxidize like this are what we call reducing sugars. That might seem a little counterintuitive to you at first. Why is it that if we're oxidizing the sugar, why do we call it a reducing sugar? And you have to keep in mind that oxidations don't happen in a vacuum, right? Every time you have an oxidation, you have a reduction. They always come in pairs. So the sugar is being oxidized, aldehyde to carboxylic acid. But in that process, the metal gets reduced. So the reason why we call them reducing sugars is because they are capable of reducing metals. All right. Any questions on that? Okay, well, what else can we do with
I
these?
have a question.
Mhm.
Do we need to memorize those four?
You should probably know the names. The reason I kind of hesitate a bit is because if you were like on the ACS final, for instance, you might see something where they had a monosaccharide and had a handful of reagents and asked you to predict the products, and you might be given this transformation and said which of these reagents could do that transformation, and they might just give you like silver and ammonia. So I'm not saying you have to memorize it, but you need to be able to recognize that these metal ions are capable of doing the
So,
oxidation.
but not for test 4.
Yeah, not for test 4. Okay, what else can we do? Well, one of the things that we talked about earlier was that if you had very simple aldehyde with one equivalent of alcohol, you make the hemiacetal. With a second equivalent of alcohol, you make the acetal. As aldehydes, monosaccharides can do the exact same thing. In fact, we've already seen that, right? We said that the linear monosaccharide can convert into the cyclic as a hemiacetal. Right? That's what we've been talking about for the last half an hour. If we add a second equivalent of alcohol here, because that is a hemiacetal, we can make the acetal. So we lost water, and now this is an acetal linkage. In the same way that the hemiacetal up here in our very simplified example was bonded to OH and O carbon, look at the cyclic hemiacetal below. The anomeric carbon is connected to OH and O carbon. Look at the acetal in our simplified example. It's connected to O carbon and O carbon. In the cyclic acetal down here, this guy, the anomeric center, is connected to O carbon and O carbon. We call these glycosides. Once you make the acetal from one of these cyclic monosaccharides, we call it a glycoside. And specifically, because we added methanol here, I would call it a methyl glycoside. All right. Oh, the other thing about the glycosides is they are not they do not undergo mutarotation because they are not in equilibrium with their aldehyde. All right. So let's just see, this is what we were talking about a minute ago. So one of the other things we can do with these, because with the cyclic monosaccharide, not only do you have that hemiacetal, but you have a bunch of OH groups. So you can make ethers out of these. So that's what this step is doing here. This is kind of just, you can almost think of that as the same thing as methyl iodide. It's just CH3 with a leaving group. So there's your CH3, and all of the rest of that sulfur business is a leaving group. So this is just going to do SN2 chemistry. You treat the sugar with sodium hydroxide, and so let's just do methyl iodide because it's easier to see. You're going to end up deprotonating all of these alcohols, and they're going to go and attack the methyl iodide, and make the methyl ethers all over the place. Protecting group strategy is incredibly important in carbohydrate chemistry because presumably what you do to one OH group, or you want to be able to do things selectively to the OH groups. You know, if you imagine, if I took this and I were trying to, I don't know, oxidize one of these OH groups. You know, presumably you're not trying to oxidize every single OH group on the molecule. So if you're just trying to oxidize one, you've got to protect the others. And so these methyl ethers are a way of protecting the OH groups. Protecting groups chemistry is very, very important and very tricky with these monosaccharides. One of the other things that we can do here is reduce. And again, this is something you've been talking about for a very long time. If you have an aldehyde, you can reduce it to a primary alcohol. And the way we're going to do this most commonly is with sodium borohydride or catalytic hydrogenation. So this can be useful just in terms of synthetically, but it can also be used to help identify a monosaccharide. This is one of the ways they used to do this back before spectroscopy. Because, imagine for a minute, let's just go back to that example of galactose. So if you were to take galactose and you were to measure its optical rotation, it would have some optical rotation. Off the top of my head, I couldn't tell you what it is. But it would be optically active because it's a chiral molecule. Once you do the hydrogenation, what would the optical rotation here be? Would it still have an optical rotation? Is it a chiral molecule? Yeah. Remember, yeah, exactly. So remember, there's a special name for those compounds that exhibit an internal mirror plane. Meso compounds. Yes, this is a meso compound. And as a result, it would be optically inactive. So back in the day when they were working with sugars and they really were trying to figure out what they were working with specifically, they would take their monosaccharide and reduce it, and if it started off optically active and ended up optically inactive, it really narrowed down their choices as to what exactly they were dealing with, because only a couple of these monosaccharides behave this way. So I have in the slide set this slide. Don't worry about this one. This is very, very old chemistry. It's the formation of these kind of compounds that are called osazones. There is a rather interesting story about this. So the reason why they used to do this chemistry is because a lot of times when working with sugars, they're kind of syrupy and sticky and hard to They're hard to work with and characterize. You know, it's hard to get a melting point of a syrup, you know? And so what they would do is they would take their monosaccharide and react it with this stuff called phenylhydrazine, and it would make these types of compounds, which are incredibly crystalline. They make really beautiful crystals that you can get the melting points of, that you can analyze under microscopes, very crystalline compounds. The problem is this phenylhydrazine is incredibly toxic. And you might remember the name Emil Fischer. He had his projections, he had his esterification. Emil Fischer did a lot of chemistry, a lot of carbohydrate chemistry. And he used a lot of phenylhydrazine, and it killed him. So that's how poor Professor Fischer met his end. His untimely demise was phenylhydrazine poisoning. So, but you know, he gave his life to chemistry, so there's something to be said for that. Anyway, you don't need to know about it because it's really old school chemistry and nobody does it anymore. All right, in the last 5 minutes that we have, we talked about glycoside formation. And we looked at it from the perspective of just adding a simple alcohol. Which you can do if you want. But the more important aspect of this is that instead of adding a simple alcohol, what if you added the alcohol of another monosaccharide? You would end up getting two monosaccharides covalently linked together. And this is the way sugars polymerize. So from an organic chemistry perspective, this linkage between the two sugars is nothing more than an acetal. Biochemists refer to this as the glycosidic bond. It is the acetal linkage that joins together two monosaccharide units. Oh, and by the way, this would obviously lose water too.
When they're in the straight form, the aldehyde or the ketone form, do they link together, or after they link together, can they break apart?
Yeah, well, the aldehyde can.
Oh, I guess because it's the one that's doing the, but that side could.
Yeah. This side can, because that's a hemiacetal. It's in equilibrium with its aldehyde. Remember, this is an acetal, which is not in equilibrium with its aldehyde.
But couldn't it just be any OH on both of them, or does it have to be the one that's the acetal, or the hemiacetal?
Yeah, the only one that can open up and be in equilibrium with its aldehyde is if it's is the hemiacetal. But if your question was, could any of these OH groups make the acetal linkage? Yes, certainly. I mean, I drew, and that's kind of a good segue into the next topic. I drew this disaccharide as the anomeric carbon of this sugar reacting with the C4 of this sugar. But it could theoretically be any of them. I mean, I could have drawn it with a C2, a C3, a C6. All of those could make a glycosidic bond. Which is why it's ambiguous to say, I have a disaccharide of glucose. You can't just say that. Because, well, there's a whole bunch of possibilities for disaccharides of glucose. Not only regiochemical, but stereochemical. Right? So by the way, whenever we start talking about putting these sugars together, one of them has always got to donate its anomeric center to the bond. Right? Because we're making an acetal. How do you make an acetal? It's a hemiacetal plus an alcohol. So by definition, if one of the pieces you're combining is a hemiacetal, one of these sugars must be giving its anomeric position. And we call these, the one that's giving its anomeric position to the bond, we call that a glycosyl donor. The other one, the one that's basically just accepting the anomeric center, the one that's giving the OH group to the acetal, is the glycosyl acceptor. So the last question I have for you, because it ties in really nicely with what Danielle asked a minute ago. By the way, this disaccharide, the specific disaccharide that I've drawn, this glucose-glucose 1,4 linked disaccharide, is called maltose. So you may have heard of it, especially if you like to drink beer. But maltose, here's another form of it. The question I have is maltose a reducing sugar? Think about what that question means for a second. When I say reducing sugar, that means, is it capable of being oxidized by Tollens reagent, Valen's reagent, Benedict's reagent, bromine water?
I think so, because it can still open up on that side.
Yeah, exactly. Remember, that's what maltose is going to look like in solution. Nothing's happening to the acetal, because remember, the acetal, the glycosidic bond, is not in equilibrium with anything. It's kind of locked in place. But the hemiacetal is always in equilibrium with its aldehyde. So in solution, this maltose disaccharide would be existing in all three forms. The beta, the open chain, the alpha. And because there is aldehyde in solution, if you treated this with an oxidizing agent, this aldehyde would oxidize. And because this aldehyde is being oxidized and taken out of the equilibrium, being removed from the equilibrium, Le Chatelier predicts that equilibrium is going to shift to make more of the aldehyde, which is then going to oxidize and be taken out of the equilibrium, and then more, and then more, and then more, until there's finally no hemiacetal left. It had all been converted to aldehyde, which all got oxidized to the carboxylic acid. Okay. So the question, is maltose a reducing sugar? Yes, it is a reducing sugar because it's in equilibrium with its aldehyde at one position. All right. And I think that's probably a good place to stop for today.
Hey, Professor.
Mhm.
So could, the second sugar form another acetal?
Which one?
Could it form another acetal?
Yeah.